talking about capacity of neural networks for lifelong learning. You asked about composable patterns.
Okay, well, thank you for having invited me here. So this talk will start with describing the Neuroidal Model, which Christos correctly located somewhere in antiquity. So some of it is old, and then I'll describe more recent things. But since in this area, kind of the first decisions you make are often the most important, it's worth describing at length why one makes these early decisions. And just starting maybe a bit philosophically, so one thing which is kind of self-evident in computer science, which hasn't quite penetrated neuroscience, is that certainly when you build artificial systems, they have to be interpreted at many different levels, and in the engineering sense, it doesn't make it's not credible that you build a system which you only understand at just one level. So in neuroscience terms, the main question is, what are the primitive operations which cortical computation may take advantage of above this single neuron level? So there are other concepts like modularity, which engineers discuss and justified, and biologists discuss. And of course, modularity can be justified on the principle of evolution. The idea of many levels is easy to justify for engineering. So for biology, it's less clear. But certainly, if we didn't have many levels of description, then it would seem hopeless to understand biology. And in particular, the approach which I take tries to exploit some quantitative tension. So posit some problem which you think biology does, but it looks computationally intractable, so how does it do it? So just as an example, very quickly, the light bulb problem. So this is the idea: you've got n light bulbs, maybe a 30 by 30 array of light bulbs. They each flash on and off. Independent. If you look at one, every second it may be on and off according to the toss of a coin. And in fact, all of them are independent of each other, except two are correlated. Maybe 75% of the time they're correlated. So the question is this a cognitive function which biology can do? Okay, so lots of light bulbs independent, except for a pair, and the question is to find the pair. So it turns out that computer scientists have looked at this. So the point is that after about log n seconds, you've got enough information to decide this question. But computationally, the problem is that, so the obvious method is to look at a pair of light bulbs and see whether, how similar they are. So this n squared is the obvious algorithm, and it's very hard to improve on it. There are improved algorithms into the 1.58, but they look complicated. So on computational grounds, one would conjecture that brain cannot do it. So in fact, of course, this corresponds to a generic correlation detection mechanism. Is the brain a general correction detecting mechanism? And so I've never heard anyone suggest that seriously. And this is consistent with the computational theory that it seems hopeless. Okay, so obviously, certain correlations, like if every time you come to Berkeley it rains, you'll notice that because it's somehow important. But if every time you come to Berkeley, the first person you meet coming out of Bart has a red shirt, probably that correlation you wouldn't notice. So the idea that for all our thousands of concepts, we go around and detect correlations. Cognitively, no one suggested it, and that's consistent with computation. So basically, my proposed methodology is similar, but now let's look at tasks which we do believe cognition does, and maybe those which look difficult, and see how the brain may do it. And this will give us some insight. And the kind of things which impress me about the brain are symbolic processing, green fox. You tell me the green fox is a restaurant. Yes, I can handle that information. And you tell me it's a bad choice. Yes, I can deal with that. It was recommended by Joe. I heard the election result there. So I can deal with this kind of lots of facts accumulated in my brain. Maybe I'll even remember it tomorrow, maybe in 5 years' time. So this ability to treat large amounts of cognitive information is what impresses me. So this is treating something on scale. So the difficulty will always come from treating things on scale, where you deal with large number of light bulbs, large number of concepts. Okay, and also important to what I'll say is this notion of chunking. So the idea is that these facts aren't believed to be flat in our brains, so we can make a compound concept out of Green and Fox. It's a restaurant, becomes a higher level concept of an equal citizen with lower level ones. So chunking is a well-known psychological idea. Okay, so so I'll describe some very basic early decisions in the Neuroidal model. Then I'll go on to more recent things, and I'll finish up with, I think, my main purpose is, which I find quite exciting, is that now for the first time I think we're close to being able to test directly whether these kind of computations happen in the brain. Okay, so so the four primitives. So the main question is, well, it's not the light bulb problem. What is the brain doing? And I think probably the choice of what your primitive tasks are is probably the main one, or the most important one. And certainly inductive learning, as in deep learning, very important. But actually in my list it came number 4, which I think is probably still the right decision. So in one sense, inductive learning is too easy. I mean, as we found out, you can do a lot of interesting learning with simple learning mechanisms, so that won't give us this quantitative tension. And the other thing is that there are even simpler things which are hard to do for the brain. And so maybe just one comment is that, so certainly inductive learning is currently practiced on massive scale, millions of examples, vast amount of computational power. That's very powerful as far as engineering, for example, because these, as in vision, these learning mechanisms pick up phenomena which probably we picked up through evolution. So as engineering, they're very good. But somehow the bigger the scale you practice machine learning on, somehow the further it gets from neuroscience, because that's not what we do. Okay, so I'm telling you about Neuroidal Model. I won't give you a million examples, and even worse, I won't. In between my examples, I won't retrain all the examples of every other concept you've learned in your life in the next 45 minutes. Okay, so just the interaction with the world which humans do, as far as inductive learning, is just very different from what the highest end machine learning things do. Okay, so inductive learning, important. So another one I call memorization of conjunctions, and this is basically learning of an instance. Okay, so if I learn the word Shakespeare, that's an instance, and this discussion, and it's a different phenomenon. Okay, so certainly when you learn an instance, there's some noise tolerance, so if I misspell some letters, I can correct it, but it's kind of the correction is probably something accidental, not particularly tuned to the word. So this one-shot learning is just a different phenomenon from inductive learning. So the people who try to shoehorn both into one and wonder why deep networks can't learn from one example, I think that's misplaced, because I think they're just two different tasks. There's one-shot learning, memorization, and there's inductive learning when you generalize, two different tasks. Okay, that's two. So third task is association. Again, that word is used in many senses. I'll define this more precisely, but it's basically when you have two concepts which you already know, and you train your mind so that whenever in the future you think of X, you'll think of Y. So we'll do that. And then the fourth task is, in some sense, the most fundamental, is how you store a concept in the first place. You've got a new concept, and a neuroidal model. Where do you put it in your brain, for example? Okay. So these are the four primitives I have been looking at for a long time, and okay. So that's the primitives, and of course these things are only of interest if I can do them at scale. Okay, so humans can do tasks which correspond to these formalizations, thousands, tens of thousands in a lifetime, and the miracle is that the earlier ones you did haven't degraded that much. Okay, so that's the miracle we need to explain. Sorry? Okay. And in big, thick neuroscience books, they've got thousands of pages, but they don't tell you how this is done. They don't explain this. It's not. Okay. That's not what they're interested in. Okay, so the neuroidal model, there are two phases of it. One is as a programming language. So your neurons as a directed graph. The communication is spikes. Now each neuron executes a little algorithm, which is local to it, which depends on the spikes it receives, and it may emit a spike. And these you can program. And so what the biological correspondence is that it's known that there are hundreds, thousands of different neurons, which are really different. They express different genes. They're genetically different. So why would you have hundreds or thousands of neurons if they weren't executing different algorithms? I can't think of why. So the idea is that evolution discovers biochemical implementations of certain little algorithms as it needs it. Fine. Okay. So looking for some universal model of a neuron is probably not the right approach. Okay. And then so one design decision which I remember struggling over is what about synapses? Maybe synapses are standard. Maybe in the brain, they buy a standard synapse off the shelf. But again, so all the attributes of the model I introduced because I needed some little programming latitude. And again, I needed to program synapses a bit more than just having this weight. And also, fortunately, now it's known that synapses come in enormous variety, genetically, etc. So this is a kind of a programming model. And the other dimension one needs programming in is time. So as we heard in Crusoe's talk and also before, so many things you have to break symmetry. So man bites dog, dog bites man. How on earth do you do that computation? And somehow you have to break symmetry. And the only method I found was using timing. So I think the brain needs hardware assist in programming asymmetry and timing. And so again, I didn't think that, so the spike time dependent plasticity, which came a few years afterwards, is of course the most beautiful instance of it, that whether you want to increase or decrease synaptic strength depends on the relative timing of the two neurons. So because you need a programming language where you can express all these things. And also there's some weak synchronization, probably riding on one of these rhythms, where basically the idea is that if we start off some computation, we see a scene, and then after step 2, 3, 4, I know what I'm doing in steps 2, 3, or 4. I can rely on the other neurons being also at step 2, 3, and 4. But the aim in the model is to underestimate cortex, so only put in these mechanisms if you believe cortex does it. Its purpose isn't to program something crazy. Okay, so I think evolution manages to make variations in the neural hardware as it needs. But what it is limited by are ultimate resources. So this is the other aspect of the model, that there's strict numerical resources. So we've got n neurons. If you want to double your neurons, you need a bigger head, probably. If you want to double the number of connections you have, so D is the number of connections to and or from each neuron. That's a very expensive resource. And the third main resource I deal with is synaptic strength. So I've got this number K, and so K20 means that that's the maximum synaptic strength. K20 means that you need K neurons firing for the postsynaptic neuron to fire. So K equals 1 means a single neuron can cause a cascade, but most neurons are much weaker than that. Okay. So K is much more difficult to measure, and we don't know that much about the distribution of these Ks in cortex. So these are all parameters for me, because we may be dealing with a part of cortex, and some of the numbers may not be known. So the fourth parameter is time. Not much negotiated about time, but the mechanisms I use are all 2 or 3 steps. So you have to be very economical in time, because your brain is slow. Okay, and why all this works is that the details of what's programmed in neurons don't seem to be the most important thing. The brain is so communication challenged. It's sparse connection, slow spikes, that somehow that's where you can get the quantitative tension. Okay, so just a slightly more detail as far as these tasks. So each of these tasks has a definition. So first time you heard of Donald Trump, must have been such a moment. So what happened in your brain? Did you allocate storage or what? So in this definition, you did do an operation, which is to allocate storage to this concept. And the definition here is in the manner of chunking in psychology, that you believe that parts of this concept you already knew. So maybe Donald is some concept you knew, and Trump you already knew. And the act you did was to allocate some more neurons to this task, to this concept, which will correspond to Donald Trump in the future. Okay, so you're born with this random graph in some state, and each experience you have, you update some weights, basically, and maybe some states. So neurons have states as well. Okay, so that's storage allocation, and this is chunking. So that's one operation. And again, we've got the circuit, and interaction with the world will modify the circuit, so the circuit behaves differently.
Question?
Yes?
That's not that straightforward. Do you have in mind the vivid representation, or can you get to that?
Yeah. Okay, so the one assumption here is that I have a set of neurons corresponding to Donald. Okay, so I'll say more about that. And so in particular, the experiments which are familiar to all of you, where people poke electrodes into certain parts of the brain and find neurons which correspond to concepts like Bill Clinton. And for example, you can, in these experiments, you find that maybe 1 in 500 of neurons in that part of your brain are very Bill Clinton-esque in a certain sense. So these are complicated, but the idea that there's this locality, that certain neurons really correspond to a concept and certain neurons do not, has some foundation. And this is the assumption of the model. Okay, so an item here corresponds to a set of neurons, set of R neurons. We don't know what R is. And then you have to make a decision whether the Bill Clinton neurons, are they disjoint from all the other concepts, or are they shared with other concepts? So you can have two different representations and algorithms. So this item is very similar to Christos' assemblies, but exactly as he says, traditionally in assemblies there's some notion that what represents a concept is somehow richly connected. And here I don't have that assumption. And so we can discuss afterwards whether that assumption, whether this strong connectivity helps you or hinders you. Okay, so I think it hinders you. I think you can do a lot without this assumption. Okay, we can defer that discussion. Okay, okay. So that was one operation. So the second operation is association, which will mean that now we're not allocating new neurons. You already have two concepts in your brain: Donald Trump, elected president, the concepts you understand, and then you need some protocol by which, if you stimulate these two concepts, A and B, in some way, the result will be that in the future, when you think of Donald Trump, you know he's been elected president. Okay, so this is very similar to the notion of heteroassociative learning, which goes back to the 60s. The association with association is used in many different senses. So here I've got definitions of each of these. Okay, so these are operations. And so in a second I'll tell you what the algorithms look like. But what the goal is, I want to demonstrate that there's some way in which we can imagine the brain does this. Okay, so a bit like the light bulb. For the light bulb problem, I know no implementation. For these, which are more cognitive, I struggle to find some. Okay, so I think what we do is that we're told an association. There may be, you're given an example of an elephant, so you refine your notion of elephants. That's inductive learning. Supervised memorization is a bit like a one-shot learning, a bit like a definition. I'll tell you what a group is in mathematics. And then hierarchical memorization is allocating a new concept. So we seem to be able to do these operations in succession. And again, the miracle is that it doesn't degrade as much as it should. Okay, well, it does degrade. Okay, so how can you explain this? So using algorithms I haven't quite described yet. And this is a setting in which things are pretty complicated. It's hard to analyze. but you can do simulations. This was done with Vitaly Feldman some years ago. The question is, what's the capacity? How many of these tasks can you do before your performance degrades? Degrades means that the earlier things you've learned are gone or confused. Okay, so it's not that easy to do. So again, we've got these 4 parameters: number of neurons, so 10 to the 8, some part of your brain, 8,000 connections per neuron. That's reasonable. K equals 16. There's some sort of synaptic strength. And then so we've got R is enormous, about 1/3 of a million. But roughly it corresponds to these experiments with Bill Clinton cells, that is like 1/500th of the part of your brain. So R could be enormous, R could be small. Different parts of the brain could have different R's. I don't know what the R is. And also I don't know what the K should be either. Different parts of the brain may use different Ks. But if you just try it off, the results are a bit disappointing. You get about 3,000 actions before things degrade. And again, I don't quite know what's good, what's human performance, what's an expert human's performance. So the Oxford English Dictionary has 500,000 words, but most people don't know that. Know all that. Shakespeare had used 30,000 words, and he was quite successful. That was enough for him. So, so probably something in the hundreds of thousands may be a reasonable aim for these tasks. Okay. Now you can get more realistic, more numbers you're proud of. Like we've got about 250,000 successful actions if we use strong synapses, maximally strong synapses. So these are synapses which are so strong that a single neuron can cause a successor neuron to fire. And whether cortex uses these, whether primate cortex, human cortex uses these is kind of open. Maybe evolution has discovered this, maybe not. But algorithmically, strong synapses are very good. I suppose intuitively, it gets more Boolean. Okay, so if we do Boolean computations, it gets a bit more Boolean. Okay, but these strong synapses is an assumption. But otherwise, everything we do is, I think, is plausible. Okay, and so so just one of these tasks I have analyzed quite seriously. I mean, it's enough to do simulations for many purposes. One, there's more detailed analysis for this is associations. So just very briefly, I'll describe that, and again, I'll just spell out why this is not exactly what people usually mean by association. Okay, so here it is one-shot learning. Every association you hear once. It's kind of lifelong learning in the sense that you want to hear lots of things, like 10 to the 5 tasks. You each hear once. So learning doesn't just mean that you learn the information so sit somewhere passively, but learning means that you finish up with a circuit which does something. So if you hear Donald, you may think of Donald Trump. Also, the sub-circuits will be composable, which means that if you hear that someone's become elected president, and you already know what presidents do, then in a flash, your cortex can follow through the implication. And this has some constraints on the algorithm. So in particular, it means that the inputs and the output sizes of the neurons have to be the same. Okay, and so the whole architecture has to be plausible. So this will be a random graph, one-way connections. And then maybe the main point is that although I'm analyzing one task, the whole point is that it should be in a context where you can implement other useful tasks. Okay, so just being very good at one task, I think, is the wrong approach. You have to be able to do a set of tasks which you think between them is useful, like allocating storage, association, some inductive learning, etc. Okay, so just to emphasize this, okay, so what the algorithm consists of is very simple. So there are 2 simple algorithms which I compare. So the simplest implementation is that we've got this random graph. A set A of neurons represents Donald Trump. A set C of neurons represents elected president. And these are already allocated. And when you learn the association, some weights get changed so that in the future, when you stimulate the Donald Trump neurons, then you will stimulate the elected president neurons, and don't do too much other damage. So there are lots of negative constraints that you don't want to do spurious things. Okay. And this is compared with a more elaborate algorithm. So, the advantage of this algorithm is that basically almost a random bunch of neurons does this. So it is evolutionarily, this is the default. So this is more advanced. So we got not a layer, but like half your neurons do no learning, but they've got fixed very high weights. Okay, and the communication between the A and the C are through these neurons. So in some sense, these are some sort of amplifiers. So A is connected to D neurons in these relay neurons. Each of these is connected to D more, so you get much more fan out. Okay, so that seems obviously a good idea. But the problem is that you're much more likely to confuse things. Because in this regime, we are going to represent every concept by a set of neurons, and these neurons are going to overlap. Okay, so there's a lot of scope for error. And so a bit more formally, so maybe X1 could be Donald Trump, Y1 is elected president, and then we've got C other associations you've learned. Okay, so the question is how many can you learn without degradation? And the number of neurons you use for your concepts should be the same if you want to compose these. And kind of the most obvious question is whether there is an information theoretic limit, roughly D times N. So you've got N neurons in your brain, D synapses into each, so it's D N synapses. So kind of the best you can hope for is that the capacity is you can have one memory or one association per synapse. Okay. So can that be achieved? Or in other words, so if you take a conventional, if the number of connections is the square root of the number of neurons, which you've already heard about, the question is, can you memorize number of correlations which grow faster than n? Okay, does it grow as fast as the number of neurons or as fast as the number of synapses? And there's also some semantics. What do I mean by Bill Clinton cells? So here there's rather extremely uptight semantics, which says that all of my neurons will fire. I only say that my set of neurons is representing Bill Clinton if all of them are firing, and then when I do an association, I want all except possibly one to fire. So it's a very strict criterion, which in real life I'm sure you can do with things which are much less strict. Okay. So anyway, so the summary is that with the simplest algorithm, random bunch of neurons, the capacity in this regime only grows as D squared, which will be about proportional to the number of neurons, if D is the square root of N. Whereas with the most elaborate one, you can reach information theoretical capacity. And so the intuition mathematically is that these concepts are these large sets of neurons which overlap, a lot of room for confusion. So when your large set of neurons A expands to your intermediate neurons, it expands even more, the overlaps will get even bigger, and it'll get even easier to confuse things. Okay, so by having this, so before you had just kind of reached, from each you could reach the others, now you can reach D squared, sounds great. But also the scope for making spurious firings grows. So this turns out to be a finely balanced phenomenon in random graphs, and it turns out that strong synapses are computationally would be very useful. Okay, so that's one possible way of explaining human performance. So there's also another way of how we can reach more convincing capacities, So it turns out that I had these 4 basic primitives, and one of the weak points was that the mechanism I use for allocating storage for a new concept, Donald Trump, the mechanism I used within Cortex has a high variance. So if I want to allocate 1 million neurons, it kind of maybe allocates 1.5 million sometimes, 500,000 other times. So you pay a high cost for that. So it seems that for that primitive of allocating storage for something new, controlling how many neurons you allocate is pretty important. And it turns out that a simple feed-forward network with the right parameters is able to stabilize the number of neurons allocated. Okay, so this is like suggesting a separate mechanism which you put on top of Cortex to help you do one of the tasks. It's not done within Cortex. Using another gadget improves things, okay? But this task which you could do better is in fact this chunking task, okay? The psychology called chunking. And when we do chunking, allocating new memory, what do you think of? Well, it's the hippocampus. The hippocampus is the part of your brain which is necessary for allocating new storage. Exactly, very similar sense to how I'm discussing it. So the obvious hypothesis, if you want high risky hypotheses, but is that in the brain is the hippocampus which does this. So the theory is that what the hippocampus does is the most basic thing is to decide where do you put something new. So if you want to memorize a new concept and there's some locality, the first problem is where do you put it? The hippocampus does it for you. Okay, so that's the. But it may do other things as well. So besides just so it would be like a hash function. It identifies the neurons you want to store it at, but obviously it also helps it to get there. So hippocampus isn't just a simple feed-forward thing. Okay, so this is kind of where the theory is. So quickly, as far as experimental validation, well, there are some very simple things which one can say. So let's say telltale predictions. So you've got a theory. It requires some things. Maybe you find it later in experiments. So strong synapses, certainly, when I first worked on this, it's obvious that strong synapses were useful computationally. Neuroscientists gave me no help in permitting me to think they existed. So even synapses of a few millivolts, they hadn't been observed. Okay, so anyway, and another kind of prediction you can make is that once you've got an algorithm, then you do have a connection between these parameters. Okay, N is the number of neurons, D is the number of connections, K is the synaptic strength, R is how many neurons you use for a concept. So in some simple systems, these things are measurable. So Gilles Laurent has a paper about 10 years ago for the olfactory system of the locust, where, for example, R is you give the locust natural odor, and R is how many neurons are excited by it. And also you can measure the synaptic strength. So for predictive systems, you can see whether these numbers fit, and for his predictive experiments, these things fit quite well. But I think what's possible now is a much more direct validation of whether the particular systems level primitives I'm suggesting are in fact what the brain is at least capable of. So, okay, so the method would be this old-fashioned word in electrical engineering, in-circuit testing. So if you've got a circuit, you can test it by giving it the inputs, outputs, whatever. But another way is to put electrodes in and seeing whether the little part does what you think it does. So why not do it in the brain? Surprisingly, neuroscientists don't like it too much because they like natural stimuli. But with natural stimuli, you've got so much going on that you're not testing what you want tested. Okay, so this would be the simplest experiment. So if these associations are described, if the brain does them, then this experiment should work. So the experiment would be that, well, you have to look in the right part of the brain, whichever part of your brain does this. So the theory is that you take a random set of A neurons, another random set of B neurons, and you stimulate them according to some protocol, doesn't know exactly what, but the result will be that in the future, when you just stimulate A, then B will become active, and not much else. You don't want too much noise. Okay, so so this would be a verification that this primitive is being implemented. Whether it's any of my particular algorithms, it wouldn't verify that, but the primitive is more important. The functionality, whether associations like this are implemented, is kind of the important thing. And exactly which algorithm is almost second order. So the difficulties here are that you have to, say for, so the B neurons, they can randomly selected, and in the training you have to simulate it, and then in recording you have to record from it. So from the same set of neurons you have to train and record from. So that's becoming possible. So the other difficulty is that we don't quite know what R should be. Should you do it on 100 neurons each, 1,000 neurons each? And depending on this number, you use different techniques, and there may be different difficulties. But there's no reason why we can't find this kind of thing out. Okay, so again, the question is whether cortex. This will test whether the cortex has the capability of doing this kind of association. Okay, so so I think that's okay. And as far as other things, okay, so optogenetics. That's how you do this. The other sources of experimentation which would shed light on this kind of theory. So connectomics, I think the main promise of that from this perspective is that we'd find out how strong synapses are. So strong synapses tend to be big. I should say that strong synapses, all I care about is the connection between two neurons is how strong the influence is of one on another. Whether it's many small synapses or one huge one, I don't care. It's the net total synaptic strength from one neuron to the other. And third kind of experiments would be, so if you've got some imaging, some recording mechanism with good timing, can make fine time distinctions, then maybe you can also get results a bit reminiscent of the natural language things about basic mechanisms of how your brain resolves the time dimension, exactly how you process man bites dog versus dog bites man. So there's several avenues where one can hope that future experiments can resolve the status of these kind of theories. Okay, so thank you.
I was wondering, what do you think is the algorithm for answering kind of meta questions? For example, same, different kind of questions. Either which of the following objects are related, which one is the odd one?
Yeah, so I should have said that all. So what I'm doing here, I think I'm looking at abstracting things which are quantitatively difficult to explain. But to make a brain work, this would be in conjunction with some working memory apparatus as well. So you're saying if someone asks me a question, are these two things similar? What do I do? So I think if you ask me any question, in my working memory, I'll bring in some information from my long-term memory which is relevant and kind of toy around with it. So presumably the answer to the question depends on some previous knowledge of the domain of what I know. You know, if you ask me whether, if you show me two pictures of dinosaurs, are they similar or not, depends on my expertise of dinosaurs whether I say yes or no, right? So I think we bring in information of this nature. There could be generalizations, there could be one-shot learning, there could be associations, but somehow, whatever question you ask me, I'll bring in the relevant information which I've learned from with these rules, and churn them over. Okay. Not sure whether that's a good. Okay, so.
So once you have all these primitives, well, let's say all these primitives working in the brain, would that be enough for the brain to do the kind of things we need to do? I mean, does that solve the hard tasks? Just crack egg?
Well, I'd argue that probably you need at least these four. Okay, so and the question is how much can you build on top of these? So the question is maybe in a computational sense, if you have these four at one level, Yeah, can you build in a computational sense everything else on top of it? Maybe your answer is no, maybe you want a fifth one or a sixth one, but I want to keep that level limited. Okay, so I don't know.
Can you say a bit more about composability? What do you really mean and why it's important?
Oh, so in the title, so that refer to particularly these associations. So the idea is that if I learn associations, then my brain, which can, you give me Donald Trump, and I've got associations about what his position is, what people in his position can do. Okay, so I can compose associations on the fly without reflection. Okay, so it means that the way you set up the circuits, it's not just you put these circuits randomly in your brain, you have to put them in your brain so that they're composable. Okay, so if the circuits are in your brain so that if you deduce that someone is president, you'll immediately be able to deduce everything about presidents.
But you don't get to the actual process of composing itself, right? You just assume the chunks, the kind of blocks. But how do you really link the blocks in a sequence, for example?
Well, no, it does, because you represent, say, notion of president by a set of neurons, and then these you're going to fire by some piece of information, and then these will be enough to fire the next association.
Not in a flexible way.
Sorry?
Not in a flexible way.
Not in a flexible way.
Not in any computation.
Well, it'll do it in some fixed way. That if you want to do anything more complicated, you probably have to bring it into your working memory and think about it. But I think you do want some minimal capability in which the circuit can, you learn association so you can compose them on the fly in your circuit. Okay, so this will do it on the fly.
But it still seems a little flat, because you appeal to hierarchies early on, and it just seems like if you adopted that in your representation, then you would be able to access the facts about a president in a sort of logical way, rather than I don't know how we're going to read these out. It seems like we could just flip them out linearly. It seems in your formalism, but you really want something that has a meta structure that you can access the associations in a more useful way.
Well, I think if you do any explicit reasoning on it, then I think you have to throw it into your working memory, and that's where you'll figure out if you want to do if you want to reach a new conclusion for the first time, you'll have new reasoning for the first time. You'll do that in your working memory, where you. But I think the question is how much can you do in your circuit without your working memory automatically? And I'm saying you can do quite a bit. And I think you do need some capability of being able to to string associations together without reflection automatically.
So what's not clear is that the association is not unique, right? So you can have a lot of things following Donald Trump. So what's not clear to me is how do you do that in your model?
Yeah. Okay. So in this definition, with each thing you had a single association.
Reflex almost. It's not real compositionality.
Well, yes. Yeah, so in more complicated situations, if you have a conjunction of things, of several in a context, you'd reach a different conclusion. Yes. So this is, if you like, it's reflex. Yes. Seeing how you can learn complicated reflexes in your cortex. Yes.
Question. To be just a little bit of a devil's advocate, I mean, the primitive, I'll just pick one of your primitives, okay, that a pattern A would cause a pattern B, and that this would be learned. I mean, that's an idea that has been. I would have called it an axiom rather than a prediction. I mean, a visual image that causes an auditory pattern, that's the name of the object. So I'm trying to see maybe William James might have said that back in 1898, and Hebb said that. So I would have said that's something that is universally accepted as a primitive in the brain, is the ability to learn an association between A and B by changing synapses between neurons. So am I missing something when you propose, and you're proposing an experiment to test whether this is really true?
Yes. Okay. So main thing I'm saying is that looking at a single primitive one at a time isn't very fruitful. You have to look at a set of primitives which I say is adequate, like I've got these 4. So I want to show that all these 4 are together realizable. So if someone shows this experiment, then the next thing is whether you can do the other experiments. I want to show in the same way that the other primitives are implementable. Okay, so I think one primitive by itself doesn't give you very much, because as you say, for example, Will Shaw studied neural nets exactly in this association sense I did, and people did before. So what becomes quantitatively difficult is if you want to do several different things at the same time. Okay.
One more question.
Yeah. I'm wondering about the storage allocation concept as hierarchical memorization. So it seems like it suggests that initially there would be empty space which would be filled with something that is allocated, or there would be the bottom of the hierarchy, the most basic object primitives, which every other potentially represented object is built up from in this associative manner.
Yeah, well, yeah.
Is that how you interpret it?
Yeah. So you're born with some sensory devices, and probably the outputs of the sensory devices, maybe a single neuron in your retina could be a primitive. And so the theory is that. So I'm sure that evolution has built things on top of it already. But so you're born with some things. So if something happens to you, some sets of neurons light up, some assemblies, okay? And then you build on top of those. You're born with some, and you build on them.
All right. Okay, so thank you.